Uh, Hi everyone. So I'm Yusuf. I'm a PhD candidate at the Department of Geology and Geophysics, University of Utah. I'm a geochemist, hydrologist who uses geochemical techniques, mostly water isotopes, to understand the effect of changes in land cover, land use, changes in urbanization, increase in population on our water resources. And I've been doing a few projects as a part of my PhD. And today I'm going to talk about one of the projects where we looked at the effect of climate variability on the water resources of the Salt Lake Valley. So when we started the project, the main aim was to see if water isotopes can be useful in studying urban water resources. The main question that we wanted to answer was, can we use water isotopes to connect the water that comes out of our tap to its climatic sources? Can we quantify how much water loss we have from our entire resources, from our entire catchment? And can we answer any other questions? So before I move forward, I would like to give a brief overview of water isotopes. I guess a lot of folks here are not very accustomed with water isotopes. So water isotopes can be thought of as fingerprints. So different hydrological systems have different water isotopes depending upon their location, such as latitude and altitude. And water isotopes are also modified by precipitation, by changes in temperature, by changes in humidity, and so on and so forth. So they act as a very good fingerprint to study water systems. So for example, if you have two samples, one is from Red Butte Creek and one is from Great Salt Lake, and we don't know which one is from what. So if we measure their water isotope ratios, we can tell that, okay, this sample is from Great Salt Lake and this sample is from Red Butte Creek. So here I show two maps of how the water isotopes vary globally. So these maps shows the water isotopes of surface water like rivers and lakes or glaciers if it's Antarctica or Greenland. So we see that few things stands out here. So the highest values shown in the red color are around the tropics, and the lowest values are as we move upward, in the Arctic region here. So we have a trend, we have a trend from high to low values as we go up towards the pole world. And secondly, we also have another trend. If you look here in parts of Himalayas or here in parts of Andes, that even though they are in the tropical region, they have very low values because they are high altitudes. And similarly, the highest values of the water isotopes, around 30, is observed in the Sahara Desert or the Arabian Desert because of the evaporation. And I will come to that later. If we focus just on the United States, we see a pretty similar trend. So the highest values are observed here in Texas region in the southern states, and then as we move upward, the value decreases. And again, the lowest values here are observed in the parts of Montana, Idaho, Wyoming, and Utah because of the high mountains present there. So water isotopes are governed by latitude, altitude, and they're also modified by precipitation and local climatic factors. So today I'm going to show the results that we obtained at a very local scale in the Salt Lake Valley. So over the last 4 years, we have been sampling the entire valley. So Salt Lake City has 18 water districts. So Salt Lake City, Magna, West Jordan, and so on and so forth. So every year we went twice, once in the month of April and once in the month of September, to get a spring and a fall signal, and we go and collect water samples. So we'll go out to gas stations, to restaurant, to businesses. We'll go and collect 5 ml of water, and then we will measure their isotopic concentration. And every sample we had more than 120. Every survey we collected more than 120 samples. So we had a very good distribution of data throughout the valley. Another thing that I want to point out in this map is, like, all these yellow districts, they are mostly supplied by the Provo River system. The blue here, the Salt Lake City, the Sandy district, they are supplied mostly by Wasatch Creek and in parts also by Groundwater Wells. And the districts in the white, they are supplied by mostly by groundwater. So I'll probably just move it a little bit upward. So this is how the data looks like. So this is for one of the surveys that we did in fall 2014. So we see that first of all, there is a large variability here just in the small region of the Salt Lake City. The highest values, isotopic values, are observed in Magna district, and the lowest values are observed here in Murray and Midvale area. Another thing that I want to point out is look at these two dots here. These two samples were collected across the street. One was in Magna and one was in Granger Hunter or West Valley. And we see a big difference between these two isotope ratios. And if we average the values observed in each district, this is how the map looks like. So Magna has a very distinct and a high value here. All these districts here, South Jordan, West Jordan, Kearns, Harriman, they have this value here is shown in the yellow color, and the districts on the east central part, they have very low values shown here in the blue color. The another point that I want to show here is that Salt Lake, Granger Hunter, and Sandy have values in between the blue and the yellow color. What it shows that are these three districts, which are also the most populous, they actually use water from a combination of water supply to this region and water supply to this region. So moving forward, what can we do with this kinds of information? Water isotopes can be used or do express the water management practices as we saw in the last slide, and indeed if you look, oh my god, these districts here, they are supplied mostly by the Provo River system. These districts here, they are supplied by their own groundwater, and Sandy, Granger Hunter, and Salt Lake City, they get their water from mixed sources, from Wasatch Creek, from Provo River system, and also from groundwater because they have such a large population. But today I'm not going to talk about water management practices because these information can be used for a lot of different things. They can be used to solve water right cases, they can use to solve contamination cases, they can be used in forensic geolocations. Today I'm going to talk mostly about what is the effect of climatic changes on urban water supply resources. As I told before, that water isotopes are affected by changes in temperature, precipitation, and RH. And by comparing the water isotopes of two different years, we can tell exactly what's happening, within the 2 years. Are we losing more water in a given year? Are we losing less water? And so on and so forth. And this is how our data looks like if you look at the 4 years. So F13 stands for spring 13, and F16 stands for fall 16. So we sample from 2013 to 2016, and we see that there are two isotopes here, oxygen and hydrogen, and they keep on increasing till 2015. And as I told before, increase in isotope ratios means there is an increase in evaporation. So from 2013 to 2015, we see an increase in the evaporation from the water resources of the Salt Lake Valley, and then in 2016 it kind of drops off, and then again in fall 2016 it goes up. So what is driving this? Why is this happening? And the answer is very, very simple. It's due to changes in precipitation and temperature. So the long-term average temperature of Salt Lake City, and this data is from the airport, is 11.1 degrees Celsius, and the average precipitation at the airport is 420 mm. And if we look at the last 4 years, we consistently have much higher temperatures. In 2013, the average temperature was 1.3 degrees Celsius higher. Same for 14. In 2015, the average temperature was around 2.6 degrees Celsius higher, and in 2016 it was 1.6. And in all these 4 years, we also had lower average precipitation. And again, going back to this slide, we see that the largest shift that we see is from fall 14 to fall 15. This is the big jump here in the isotope ratio that suggests that the largest evaporation occurred from fall 14 to fall 15. And this is again clear from the temperature data that we see that in 2015 the average temperature was 2.6 degrees Celsius higher. Another thing that I want to point out is that the deviation in the precipitation is not consistent, and it does not follow a pattern. So we have the lowest precipitation in 2016 water year. However, if we look back here, in spring the isotope ratios drops. It suggests like, okay, is there a decrease in evaporation, and then it goes up. So this year, last year in December, January, and this year, February, we had pretty decent amount of rainfall. So these rainfall, winter precipitation actually recharged the water resources in the Salt Lake Valley. But we had no rainfall at all this year. In the spring we had very less. But if we look at summer and fall, we had very, very less rainfall this year. And that's why the overall rainfall was very low, but we did not see a lot of evaporation. What this suggests is that temperature is a dominant factor when it comes to evaporative loss of water, not the amount of precipitation. So it might happen that in a given year we might have less precipitation, but if we have much higher deviation from the average temperature, if the average temperature is much higher, we will lose more water due to evaporation. So I wanted to quantify how much water did we actually lose. So isotopes can be coupled, and there is a model called Craig-Gordon model. I'm not going into details of those modeling, but based upon other factors such as temperature, RH, we can use isotope data to actually calculate how much evaporation occurred. And if we look here from 2013 to 2016, these are the average temperatures. This is the amount of water we lost. So in 2013, we were losing around 1.6 billion gallons of water due to evaporation, which increased to almost 4 billion gallons in 2015. So compared to 2015, we were losing additional 2.5 to 3 million gallons of water per day from the Salt Lake Valley public supply system. And this is a lot of water. Only Salt Lake City and Sandy uses more water than this. So this is like the third largest consumer if you look at the entire valley. And this also leads to loss of around $2.25 million in revenue to the water managers. So moving forward, I wanted to look at, okay, is this loss of water similar across the valley? Because we know that in Salt Lake Valley, our water comes from the Provo River system, our water comes from the Wasatch Creeks, and also from the groundwater wells. So we use a statistical clustering, that a technique that groups together sites that have similar isotope ratios. So all these sites are grouped together in the green color because they have similar isotope ratios and they are supplied by the Provo River system. And these one in the blue here are grouped together because they are supplied mostly by groundwater wells. And the yellow one here are supplied by Wasatch Creeks. And if the supply from Wasatch Creeks is low, they supplement their water either from the Provo River system or from the groundwater wells. So let's look at the groundwater data here. So we look at the groundwater wells and we don't see any increase in the isotope ratios, which I showed you guys a couple of slides before. We don't see any increase. So this suggests that there is not a lot of evaporative loss from these systems, and that is obvious. Groundwater does not experience evaporative loss, right? So it did not we were not surprised. And also the average mean residence time of these groundwater wells is more than 12 to 15 years. So we don't see the pattern that we observe in the overall Salt Lake Valley distribution in these groundwater systems. So moving on to the surface water resources, we see a big increase in the isotope ratios over the time period from spring 13 to fall 15. And that's obvious, right? Because these are open water sources, and during warm, dry years, we expect large amount of evaporative loss from them. And also these surface water resources actually supply majority of the water within our valley. They actually amount to close to 80 to 85% of the total water is supplied by the Provo River system and the Wasatch Creeks in our valley. So I applied the same modeling technique that I did for the Salt Lake Valley on the Provo River system, and I calculated how much water are we losing from those systems. So similarly, we observed that we are losing a large amount of water. And if we look at if we compare these two fluxes, almost 75% of the total loss that we observe in the Salt Lake Valley is actually from the Provo River system. And this is also obvious. The Provo River system consists of two large reservoirs, the Jordanelle reservoirs and the Deer Creek reservoirs. And during warm summers, they provide ample surface area for water to evaporate, and that's the reason why we see such large amount of water loss from these systems. And this is one of the examples from Southern California. As you know, they have been going through extensive drought over the last 10 years. And they calculated that if they cover their reservoir with these black balls, they would save almost 300 million gallons of water per year from evaporation. And that will help them save or, get more $250 million. So evaporative flux is something that's very, very important, especially when we don't know how our future will be. So that brings me to the question, what about our future water resources? We have been hearing in a numerous talks today that the population of the Salt Lake Valley is going to double in the next 40 years. And the water managers, they plan to develop the Bear River system to supplement the water resources. And we looked at the Bear River system over the last 4 or 5 years. And if we know, the Bear River systems also consist of the Bear Lake. So during the high flow springtime, water from the upper Bear River is transferred to the Bear Lake where it's stored. And during the month of May, June, July, August, September, when we need more water for agriculture or for use, it's supplied back from the Bear Lake into the Bear River, and then it's used. So we analyzed it, and we found that over from a period of 2011 to 2015, the Bear River flow at the Idaho-Utah state line was 25% lower than the long-term average. And what was the reason for it? The most important reason was that there was less amount of precipitation during the last 4 years. That's obvious. But because these river systems also have numerous reservoirs on their course, there was also a large amount of evaporative loss. And we did some isotopic estimates just for the Bear Lake itself, and we were surprised that almost 20% of the water within the Bear Lake is lost due to evaporation. That's a large amount of water. So what implications do we have for future water management practices? So the population is going to increase, and it's going to double in the next 40 years. Most of the climate model predicts that by 2050, the average summer temperature will increase by 1 to 3 degrees Celsius in this region. So Salt Lake communities and will have continued exposure to evaporative losses. In future, evaporative losses can almost be up to 10 to 12% of the total water resources that we have. So far, water managers have not taken into account the evaporative fluxes, but considering the fact that we are planning to develop additional surface water resources to cater our needs, we need to be more careful, and we need to take into account the evaporation flux, and we need to develop planning that would reduce water loss due to evaporation. So I showed that groundwater does not show a increase or effect of evaporative loss. So is groundwater recharge a good way to go? Can we just like not build reservoirs and recharge the groundwater, and can it be helpful? The answer is probably no. Salt Lake groundwater is generally very contaminated. We have numerous reports from USGS and from other scientists that all these wells, they show contamination, they show signals of anthropogenic compounds, and they are contaminated. And that's the reason why Riverton Water District actually shut down all its well 2 years ago and shifted to Provo River system. The Brigham Canyon water treatment plant uses process such as reverse osmosis and has to use ultraviolet treatment to clean the water before it's supplied. So it makes the water very, very expensive. So in my opinion, artificial groundwater is not the way to go. So to conclude, I would like to say that water isotopes provide a novel technique to study urban water systems. And we saw a significant increase in water losses due to evaporation during unusually warm, dry years. And for future water development, we need to incorporate these losses, and we need to take care of this if we really want to develop a sustainable water resources plan for future. So to end, I would like to show this image, which is also there outside. This compares the image of Great Salt Lake, and specifically the Farmington Bay from September 2011 and September 2016, and we see that there is absolutely no water. The main reason is because we had less precipitation, of course, and also we are using a lot of water for agriculture and our own uses. But there is also a component called evaporation. This, due to warm temperatures, we are also losing a lot of water from evaporation, and that's why we see that today we absolutely have no water left in this region of the Great Salt Lake. And with that, I would end my talk, and I would like to take any questions that you guys have. Yes. No, of course, evaporation is a very important part of the water cycle, and we do need it. But we would technically love to have all the evaporation from the oceanic sources, right? But that's not the case. And even if we just focus on the Salt Lake in the Great Salt Lake Basin, if all the evaporation occurs from the Great Salt Lake, it goes up to the mountains. The rain falls there, the snow falls there, and then it comes down. We use it, and we transfer the water back to the Great Salt Lake. That will be the most likely or the most liked scenario. But like the evaporation that's occurring from the reservoirs that are primarily built to serve us, it's not good for the people living in the region. Yes. Yeah, I mean, it's counterintuitive. When I saw that images, so she asked about the black balls that I show in California. She said that she heard that they were a failure. And when I saw that image, I felt the same. I was like, why are they putting black balls, right? I mean, that will increase evaporation and not decrease, right? But the reason was actually they were not increasing evaporation. And secondly, they were stopping bacterial growth in the water. So there was two purpose to serve there. So that black balls had some oxide, I don't know the exact chemical which it had, but that, because once it's covered, I mean, they were expecting a lot of bacterial growth and so on and so forth. So that was stopping the bacterial growth. And I've not followed up on that image, so I don't know if it in reality it was actually a failure or a success. I have to go and recheck. Right. Yeah. Yeah. Yes, please. I'm not expert on that, but I'll try to answer that. One way to clean is we should like use less fertilizer. We should like divert less dirty water in. It's mostly the contamination is from us, right? So we should try to use less contaminants. That's the best way, to let it get cleaned, I guess. Hmm? Maybe that's hard to tell. I don't know if. Hmm? No, I don't think so. But it will be a really good thing to compare if we actually not build reservoirs and if we recharge the groundwater and see if it's a better option to clean it, or I don't know for now. Yeah, I've heard that, because I'm from India, and in India they do it. They cover the river sides with solar panel in a lot of places to stop evaporation. Yeah, but here in our case, there is no evaporation from groundwater, so it's mostly from the surface water resources, right? So that brings it to the Wasatch Creeks and to the Provo River system. And again, Wasatch Creek, the evaporation is not that high, because it's at the base of the valley, right? I mean the canyon. So the majority of the evaporation occurs from the Provo River system, and that too, there are two paths. First, like the snow, sublimating, and then from these two reservoirs, the Jordanelle and the Deer Creek. And I don't know if people here would like to cover their reservoirs with solar panels, so that will cause a lot of problems, I guess. Yes, please. So yeah, I mean, if we put more water in the ground, like one some research have shown that in the next few years, next few decades, we'll have less snowfall, we'll have more rainfall, and and it will be more flashy in nature. So we can just redirect them towards the groundwater, and artificially recharge the groundwater, and that will of course lead to a decrease in evaporation for sure. But like I pointed out, the problem with the groundwater is that it's very contaminated, so to clean them up will be quite costly, if we use it for our own uses. Yes. Right. Yes. No, absolutely. That's a very good point, and that's right also. And if we can do that, that will be great. But I read a report from USGS. It was published like 10, 15 years ago, and they showed that they had two studies, one done in 1980s and one done in early 2000s. And what they showed, that there was a trend of transport of contaminants, from the western side of the valley towards the eastern side. So if we can do that, if we can protect our eastern side, where all these recharge occur, it will be great, and then we can probably use that way to, I mean, the water will not be that contaminated. Yes. Yeah, thank you for your point. I didn't do that.
Yeah.